Hello, I'm Ronen Dar, co-founder and CTO of Run.ai. In this talk, we'll discuss how AI development is different from traditional software development and cover new requirements for AI as it relates to compute and data management. We'll discuss a new concept called continuous training that has become important for CI/CD pipelines in machine learning deployments. We'll go over the required AI infrastructure stack and present a case study on rapid AI development with continuous training automation. So let's start with the requirement for AI. Artificial intelligence is a completely different ballgame compared to what we've seen until now in the tech industry in terms of development and productization of software products. It combines three major components: data, algorithms, and compute, each bringing new challenges to the enterprise. Data becomes critical for business success, and challenges around the acquisition of data, management, and maintenance of data becomes highly important. Statistical algorithms, models, are the core engine of AI solutions, and new challenges arise around the development of such models, maintaining and retraining them in production, and ensuring things like model accuracy, explainability, and fairness. Very importantly, in the new AI era, computing power becomes more important than ever. Hardware accelerators, like GPUs, and methods for distributed computing are essential for bringing massive computing power to the hands of data scientists and researchers responsible for innovation in AI. The recent breakthroughs in natural language processing with the creation of gigantic statistical models like BERT and GPT are great examples for how data, algorithms, and massive computing power are combined to create powerful capabilities and essentially a new world where computers can understand and generate text. So if we examine the process of creating machine learning models at a very high level, it includes the following three parts. The first is of acquiring data, ingesting it, storing it in a way that different functions in the organization can seamlessly access it. Once data is accessible, data scientists can work on the data, manipulate it, and essentially prepare data sets that can be used to train models. At that stage, data scientists experiment with data and models, typically building their models and programming their training scripts. At the training phase, massive computing power is consumed to train models, optimize them, and tune their hyperparameters. Distributed computing is often being utilized at this point. The trained models are then moved to testing, validation, and then to production by machine learning engineers or MLOps engineers. So machine learning is different from traditional software engineering in the sense that it involves new workflows like experimentation and model serving. In each stage, the requirements in terms of computing power and data management are different. In terms of demand for computing power in data science teams, what we see is a burstable usage profile in the build and training stages. Researchers and data scientists consume 1 or 2 GPUs when they are building their models and experimenting with data, and then use massive amounts of computing power when training models. For example, in what we show here, user 1 is idle for weeks in terms of consuming GPU power, but then running multiple jobs on more than 20 GPUs for more than 10 days while doing hyperparameter optimizations. User 2 runs multi-GPU training jobs on 16 GPUs for days, and then uses just one GPU regularly for more than 2 weeks. Same patterns are shown for users 3 and 4. On the other hand, inference services run for a long time, utilizing the compute resources in short bursts when new service requests arrive. Machine learning brings new requirements also in terms of data management. Large data sets are frequently used by data scientists and ML practitioners to train models, simplifying access to the organizational data and providing tools for researchers to seamlessly create and share data sets and features becomes increasingly important as the organization scales and more people are experimenting with data. Caching data sets and managing their storage location can help in automating the training process and ensuring the highest throughput performance. Tracking, versioning, and managing data sets, features, models, and training artifacts are crucial for reproducibility. Machine learning reproducibility is a huge and non-trivial topic. It is important for organizations. For similar reasons, reproducibility and source control are important in traditional software development. However, unlike software development, the process of developing machine learning models is experimental in nature and involves statistical aspects that make the ML development process hard to reproduce. In inference, data validation and tools for performance monitoring are important for detecting anomalies in incoming data or drifts in model performance when the statistics of the incoming data is changing. In these cases, models lose their accuracy and need to be retrained. Now, the challenges relating to compute and data management in the different machine learning stages become even more significant when the organization wishes to automate the process of deploying and managing machine learning in production. The process includes classical continuous integration and continuous delivery methods known from the world of software development. But they also include a new and important concept called continuous training. The concept was born from the need to maintain the accuracy of models in production and retrain them frequently when detecting performance degradation or on scheduled events. Continuous retraining models in production requires the automation of a pipeline that extracts and prepares new data, validates it, trains the model on the new data, and then evaluates and tests the performance of the new model before moving it to deployment. Automating the entire process requires the orchestration of complex pipelines and the automation of compute provisioning and data management. So we've discussed the requirements for AI. Now let's discuss the components needed for building an AI infrastructure. Like any modern computing infrastructure, AI infrastructure also has a stack composing the following 3 pillars: hardware, software, and the application. The hardware includes the computing resources, storage, and networking needed for processing AI workloads. The software pillar runs the layers responsible for managing the hardware resources and orchestrating the workloads, including traditional software components like operating system, file system, networking virtualization, and more. Different tools then run the applications that utilize the hardware resources. In the AI infrastructure case, the application layer includes tools and services for data engineers, data scientists, ML engineers, and operation engineers. In what follows, we'll dive into the details of the hardware and software components. In terms of the hardware stack, it typically includes a centralized storage system for the organizational data. Data pipelines are built to ingest and pre-process new data collected from different sources. Different functions in the organization, from data analysts to business intelligence people, can then get a controlled and seamless access to the data. Data scientists, in specific, are typically accessing the data pool to create sets of data samples that can be used for training models. The training data sets are then moved to a typically smaller storage connected to a cluster dedicated for training models. The cluster typically includes GPU servers with networking that interconnects all the GPU servers to the shared storage. Data scientists can then stream the data sets to the GPU machines to train their models. One very important thing to note when it comes to AI infrastructure is speed. Hardware accelerators like GPUs need to quickly process massive amounts of data, and so storage and networking need to be very fast as well to stream the data fast enough to the GPUs without creating bottlenecks and leaving the GPU idle waiting for data to arrive. Networking between the GPU servers also need to be sufficiently fast for supporting training at scale in scenarios like distributed computing that require data movement between GPU servers at super speeds. In terms of software, a critical component in the AI infrastructure is cluster orchestration. It acts as the glue between the hardware resources and the running workloads. Cluster orchestration is particularly important for creating a shared pool of GPUs. Orchestrating jobs via a centralized system while monitoring usage and allocating resources automatically to different users and different teams according to predefined policies are critical capabilities when it comes to managing a shared infrastructure. And as mentioned earlier, data scientists have a burstable profile of compute consumption, and AI workloads have different computational needs. And so dynamic resource allocation is critical for operating shared GPU clusters. It can eliminate static GPU assignments that often create bottlenecks and long GPU idle times. Sharing GPUs and orchestrating them dynamically can bring huge gains in efficiency, hardware utilization, and user productivity. One important thing to note here is that the AI ecosystem is built today around cloud-native technologies. Containers are widely used by data science teams, researchers, and ML engineers around the world, and many of the AI tools offered today by different companies have a built-in integration with Kubernetes. NVIDIA GPU Cloud, NGC, is a great example for the adoption of cloud-native technologies in the AI space. It has gained great traction from data scientists and ML engineers around the world thanks to the extensive catalog of containerized tools, pre-trained containerized models, and software components needed for Kubernetes orchestration. But Kubernetes was built for orchestrating containerized services on commodity CPUs, not for compute-intensive AI workloads running on specialized hardware accelerators like GPUs. So there are challenges when it comes to operating shared GPU clusters for AI. Important capabilities that are missing and are critical for shared AI clusters are things like advanced queuing, fairness scheduling, dynamic job preemption, and more. Orchestrating workloads to run on fractions of GPUs, sharing GPUs dynamically, and optimizing topology assignment are additional capabilities that are missing today from the upstream Kubernetes and are important for the efficient utilization of shared GPU clusters. Gang scheduling and capabilities like reserved instances and backfill scheduling are required for operating clusters in which large distributed jobs run across nodes alongside small jobs running within a node. Kubernetes does orchestration at the pod level and not at the job level, which becomes a problem when running multiple jobs where each is composed of multiple pods running across nodes, like in the case of distributed deep learning training. Managing such workloads at scale, scheduling them in both public and on-premise environments can be extremely difficult in Kubernetes today. Another important software component in the AI infrastructure relates to storage and data management. A shared file system allows the storage to be accessible to all compute servers, which essentially allows to abstract the compute resources from the workloads in the sense that each workload can run on any machine in the cluster without being constrained by the location of data in the cluster. This brings better efficiency in terms of orchestration and utilization of the cluster. Data management is another important software component responsible for the challenges we mentioned just before, and also for challenges like caching data sets in hot storage, moving cold data to the slower storage, and things like that. To summarize, in order to ensure scalability and high performance, an AI infrastructure stack typically includes the following components: hardware accelerators optimized for high-speed parallel computing. NVIDIA's GPUs currently dominate the AI landscape. A shared data storage solution optimized for fast throughput that can keep up with the GPU's virtually insatiable demand for data. A software layer for optimizing the management of datasets, features, models, and artifacts. A network infrastructure that delivers very high performance and ultra-low latency across a lossless fabric. A set of data science tools to support the development and deployment of ML, DL-powered applications and services. And finally, an orchestration platform that stitches together all components of the stack and seamlessly synchronizes and manages resources and jobs. In the following case study, we show how an automotive company has gone from siloed GPU servers with an average of 20% utilization to a shared AI infrastructure with around 80% utilization. Run.ai solves many of the challenges we've said before. Challenges with Kubernetes in orchestrating AI workloads, experimentation challenges and sharing GPUs between different types of workloads, challenges related to controlling and monitoring usage and managing policies and datasets. By creating a shared pool of GPU resources and then completely automating the processes by allocating resources to workloads, Run.ai optimizes GPU infrastructure and greatly improves speed of AI initiatives. This case study will help to explain the specifics. The automotive company is invested deeply in the development of autonomous vehicles. obviously doing a lot of AI and computer vision using DGX servers. Tens of researchers, data scientists, as well as engineers and ML practitioners are utilizing the GPU servers, some on a daily basis and some very infrequently. The company is working with a state-of-the-art AI infrastructure stack with all of the components we mentioned before. GPU accelerators optimized for high-speed parallel computing from NVIDIA, a distributed data storage solution optimized for fast throughput from NetApp, a high-performance, low-latency networking infrastructure, and an orchestration platform that stitches together all components of the stack and seamlessly synchronizes and manages resources and jobs. The data science teams have been working in silo, each with its own exclusive small number of GPU servers. The following plot shows the GPU allocation and utilization of one of the teams. Allocation is high, meaning that all GPUs are assigned to users. However, utilization is below 20%. The first step towards increasing the efficiency of the infrastructure involved the pooling of the GPUs into a shared cluster. That allowed the cluster administrators to monitor the usage of the cluster from a single location and get policies around resource allocations. In this slide, you can see the automation of tens of jobs. Those jobs are simply queued and launched by the system when resources in the pool become available. Jobs are managed dynamically by the system according to predefined policies, using automatic preemption and job resuming to ensure fairness between users and maximum cluster utilization. This slide shows a list of experiments for hyperparameter tuning running through our system. Each experiment creates automatically thousands of training trials, while our system makes sure that there are always tens of trials running in parallel. For example, one experiment included 6,912 different training runs, each using a different set of hyperparameters. Our system made sure that there are always 32 trials running in parallel. When one trial ended, our system queued another one automatically. This simplified processes for the data science teams and brought great efficiency in terms of what the infrastructure supports. Additional automation was obtained with the integration of Kubeflow, an open source machine learning platform dedicated for running machine learning pipelines on Kubernetes. Using Kubeflow pipelines, users could create and schedule pipelines for retraining models in production. That brought more efficiency to the ops teams and allowed them to set policies around production workloads and automate the process of running low priority pipelines in the same cluster together with higher priority workloads. Visibility is another important tool that lets researchers get access to more GPUs. By providing visibility into GPU availability, users can plan their jobs accordingly and size correctly the number of GPUs for their jobs. Overall, by pulling the GPUs into a shared cluster and using Run.ai automation to let researchers and engineers queue jobs and seamlessly share the GPU clusters, the organization has experienced gradual increase in GPU utilization and in the number of jobs submitted to the system. We saw weeks with the cluster being almost fully loaded with average utilization of around 80%. The data science and ML teams have become more productive and were able to move faster in research and development. That's all. I would like to thank you for listening to this talk and invite you to visit our website at www.run.ai. Thank you.